what we can do in overfitting if the deep neural network is overfitted, and mostly we'll try to see all the concepts which you have learned in the theory lecture. Now we'll try to implement them, and we'll learn how we can like make all the concepts in a systematic way when we want to develop a machine learning model. So I will, in starting few minutes, I will start with some objectives of this session, and then I will show the code, and then we'll learn how we should go for training any model. Okay, so first question that comes to our mind is whenever we train a model, okay, and we get some performance, like let's say 90% of the testing accuracy. Now what to do? So this is like whenever we develop a model and we get 90% of the accuracy, and now we have to decide, okay, see that whether this is the maximum performance which we can get from the model, or there is still scope or possibility that we can further improve this model or not. So we have to show that given any, given the data, you have the algorithm, and then you somehow apply some algorithm and get some accuracy. Now it is important to understand that what is, if there is any problem, or we can further improve the performance or not, or yes or no. So that's the important concept that we'll learn through the bias and variance of the model. Okay, so this is to understand the systematic approach is the objective of this lab through bias and variances. Okay, in general, the steps is first we try to fit the training set well with the cost function, and then we use the development or validation set on the cost function, and further after developing the model, after several iterations and training of the model, we see that how it works on the test data, and objective is to develop the model. So mostly we'll see these four kind of situations, in which first is like, let's say we have a training error of 1% and validation error of 11%. So the first thing is training model. So when we train the model, we see that, okay, the training is done properly or not. If, for example, training is done properly, that means there is very low bias. And there is, let's say, validation error of 11%. So the first situation is of high variance. It means the training is good, but the model is not generalized, and there is a high variance in the model, and the model is overfitted. So we have to understand what are the available options to deal with the overfitting. So whenever we develop a model, we'll see out of these four situations. In the second situation, let's say the training error is 15% and development or validation error is 16%. So in this case, we can see the training is not good. So there is a scope of further improving the training part. So we see that this is the situation when we have a high bias. The training is not good. The objective should be further first see to improve the high bias. So reduce the bias basically. Okay, so third situation, this is the underfitting situation. And the third situation, when we are not able to do that proper training, and the validation error is also very high, it means there is a high variance and high bias. So this is the third situation. And finally, in which the desirable situation in which we have low bias and low variance. Okay. So what we can do in order to make a model low bias and low variance. So these are the options. So first, what we can do is we can collect more data. Second is we extract more features from the data. Third is we collect more diversified training set. Fourth is that we train the model algorithm like longer, like higher number of epochs, and we do more training. And another is optimization function. We change the network architecture. We make the changes in the number of layers, number of neurons, number of parameters, and we can also see different regularization methods like L1, L2, dropout, and so on. So all these are the options which we can use when we find out if there is a problem in the model. Now the objective of this lab is to understand the sequence and the strategy. that which approach, which method we should follow and when. So that is our objective, and I will try to start with the first method, in which I have assigned, like designed two algorithms, two codes, in which first is to understand the bias, if the model is high bias, and then what are the operations which we can do, and another is an experiment in which we'll see that the model is overfitted, then what we can do. Okay, so for this I am coming to this notebook. Is it visible?
Yes, it is visible.
Okay. So this is an example which I have taken. The objective of this is like handwriting digit classification data set, in which we have the images of digits in between 0 to 9. Uh, okay, and I have taken 10,000 images for training and 2,000 images for validation. And the architecture which I have taken is with two hidden layers of 512 neurons each, and the objective this network architecture I have taken purposefully to make this model overfitted, because see, given this small data and complex number of neurons are very high, 512 in two layers is number of parameters very high. And now we'll train this model and develop this model and then train it and then see the situation. Okay, so let's start with implementing this. And if you want to run this in your uh, system also, I am sharing this collab link with you, so everyone of you can also try along with me, but I'm not able to see the chat box.
Maybe you can stop sharing and then share.
Okay,
Yeah.
okay, this is the first link, first notebook, first experiment, and this is the second experiment which will. Okay, so now see, this is initially I imported all the libraries, and then this is the code for loading the data, MNIST data uh, from inbuilt libraries. And then I'm taking 10,000, 1,000 samples, okay, and later we'll improve this also. Okay, we can try different combinations of data. I'm using less data. And now this is an architecture which I'm trying to develop is, firstly I'm doing this flatten. So all the features, input features, 28 by 28 image, it will be flattened in one feature vector, and then this will be feed into this dense layers and this. So I'm starting this with a small network. Okay, a second. Now if I run this, okay, and I'm also using gradient descent for optimizer, and then loss function. Okay, and this is for training the model. Okay, and then evaluations and plotting. I'm sure this code is very easy to understand. I'm sure you will be able to easily understand that what is the written. If you have any problem, you can ask. Okay, so oops, yeah, sorry, that was another bias one. I'm sorry. So this is the network 512, and then okay, when I run this, it will take 1 minute. Not so now observe that what is the performance we are getting. So you can see that the training performance is starting from 88, 95, 97, and validation accuracy is 95, and validation loss is starting from 0.21 to it is decreasing. Okay. I recommend you can also, everyone will should also run this code and then see there might be slight differences in the performance which I'm getting and you will be getting, and then it will be nice to understand that what is the behavior this network is doing. Okay? Please let me know if you have any questions so far or in between, because this is not a lecture, it is a lab session. If you will be having any doubts, so it will be nice to have interaction in between. Okay, so that will be very useful for everyone. Okay, and now see that the training accuracy has reached to up to 95, or sorry, 99%, and the validation accuracy is also increasing, but still there is this gap. So if you remember the concept of overfitting, the difference between the training performance and validation performance and eventually the test performance is high. So that is uh, the thing, and we can see that it is trying to overfit the model and training accuracy is becoming very high, and there is very that difference between the training accuracy and validation accuracy is also different. I can see that it is almost reached to 100% of training performance, which is not the, like, and the validation accuracy is still 97. So the training is increasing, but there is no performance improvement in the validation part. So it means the model is started being overfitted. Okay, now we are almost completed with the training, and okay, now you can see that the curve, the loss curve, in which you can see that initially the training was very nice, but later on the validation performance is not stable and it is not decreasing. And in the accuracy graph also you can see that the training accuracy is increasing with epochs and the late, but there is still a lot of difference between the training performance and the validation performance. So it is a clear indication of overfitting, and it is also not desirable to have these kinds of spikes. These spikes like is indication that there is no stability in the in the model, and when we develop the model, use this model, then it will have like high variance in that sense. Okay, and also observe that performance of the testing data, which is 96.77%. Okay, so now we have this model which is overfitted model. Now we'll try to understand that what we can do. So this is a situation in which we talk, like first situation in which we have some training performance and the testing performance. You may think of like 96% is a good performance, but this is not true, because there is still a lot of difference between the training performance and the testing performance, and the graph shows the indication of the overfitted model. So what we can do, as we understand, like learn in the theory lectures, that we have First, regularization as a very important method for dealing with the overfitting problem. So in this example, what I have done is I have uh, used L2 regularization here in the model, and I have kept all the things similar to the previous model so that we can see the impact of the regularization on the same model, same data, everything is same. The only difference is I've just added L2 regularization. And when I run this, I'm not running this because it is taking a lot of time. I think you can later on run in your system and then see that what is the performance you are getting, because of saving the time. And in the last, if you'll have some time, so we can also run. But I've run it just before the this lab, so we can directly analyze the impact of regularization. Okay, so this is the code for the network, and now I've used L2 regularization. Everything else is same, and then I train this model. You observe that what is the performance. Now you'll see that the training accuracy is starting from 90 uh, 988, and it is the validation accuracy is 91, and validation loss is also decreasing. So when you'll see that after the completion of this model, you see that the maximum training performance is 98%, and validation loss is also decreased. And you'll see, okay, you can observe this graph that and now after observing this graph, you can see that the difference between the training performance and validation performance is improved from the previous example, but it is still having overfitting. So overfitting problem was there, but after using the regularization, still it is not sufficient. Now what we can do? Okay, so and also observe the testing accuracy. So even if we have used regularization, the testing performance is in decrease, which is very interesting. We'll talk about it later also. Is decreased. This is one observation, and the second is that the overfitting problem with this graph. You can see that it is improved, but still there is a lot of spikes, and there is still a gap. So what else we can do is let's try to try different methods. So one thing that we can do is overfitting model means that model is complex, large number of parameters are there. So we'll see, we have seen one method, that regularization, L2 regularization. We can try L1 regularization also. Okay, and one another method for overfitting is dropout. So in this example, so all these interpretation I've written already, so I'll share this. I already shared with you. You can easily see all the interpretation. And now in this, I have now added a small dropout. Okay, so concept of dropout regularization, I'm sure you have already discussed uh, in the lecture. Now let's understand that if we increase the like if we have the dropout as a regulation method to deal with the overfitting problem, then what we see. Okay, apart from that, everything is same from the previous example. I want to show you the impact of the dropout, small dropout 0.2, along with regularization, L2 regularization for overfitting problem. Now let's see that what we get. Okay, so let's first observe that how we started the training started with almost same performance which we have seen in the previous one, and it increased training performance up to 98, almost similar to the previous. So we can see that the dropout has not contributed much because it was very small, 0.2. So now is what we should do is either we should go for another overfitting technique, or we can try with different value of the dropout. So we can try with improving or increasing the dropout value, or we can also try different methods. So we'll see later in this uh, notebook. But what I'm trying to do now is I will increase the dropout value. So from 0.2 to I will make it 0.4. Another thing that you can observe is the testing accuracy. Testing accuracy is decreased as compared to the first model, which was the overfitted model, without that training, without regularization and dropout. And still there is this high gap, and what we desire is the testing, validation testing performance. It should have a straight declining graph. And spikes means there is no stability in the model, and it is possible that you may have some, not standard or reliable performances. Now I'm increasing the dropout value through 0.4. Okay, and apart from this, I am keeping all the values to be same, all the parameters to be same, and everything is same. Now let's see that what will happen if we increase the dropout value 0.2 to 0.4, and we'll try to understand that how increasing the amount of dropout is helping in dealing with the overfitting problem. And this is the code for plotting. Okay, now let's see what is. Now see, observe this, that when we increase the amount of the dropout, the performance is started with almost 92. Earlier it was 94 approximately, so it is starting from slightly low value, and now it is increasing with some training, and we have reached to 96% of the training, and validation performance is 95. So it has like quite good in terms of dealing with the overfitting problem. There is a very low difference between the training the model and the testing the model. Okay, so by increasing the dropout, we are further decrease the amount of overfitting. Now there are some spikes, so now we should further try to deal with this. But we know, okay, this is the situation when we have very good training performance, very good testing performance, and then we can also try to reduce this overfitting situation, which is very low amount of overfitting in comparison to the starting one. So now I will again increase this over dropout value to 0.5, and then let's see what happens. So now it is starting from 81 to 91% of training performance, and then we increase the training, and then finally we get 95%, and validation accuracy is also almost similar. And you can see that there is very less difference between the training performance and the testing performance. Now the question is this model a good model? See, there is no overfitting this model, almost no overfitting. There's some spikes, but this model is almost without overfitting, because of as you know, the definition is the training performance and the testing performance model is doing good, 95% of performance for the training, and then almost 95% in the testing. Okay, so in your opinion, you will think and that this model is not overfitted. Now what we should do next? Is this a good model for this problem, or we should try other things also? So now first thing that should come in our mind is, what is our objective? Okay, our objective is for developing a model is to make the model as good as a human can do, which is called as best performance which we can achieve with a model. So for this example, let's say the model, like for if a human do the same thing and we get let's say 99% of accuracy. So our objective is try to develop a model which can also achieve 99% of accuracy, testing accuracy. But for this example, let's say the highest human performance can be 100%. So the thing is, the model is good in training, model is doing good in testing, but still there is a scope of further improving the training performance along as well as the testing performance. Okay, so we'll see what should be the strategy. But at this point of time, what I'm trying to explain is, given a model with let's say a model which we have seen in this example, what we try to do is, first we try to improve the training performance. First step is, if the model is having very less performance, it means there is high bias. So first thing is, we try to improve the training performance, which in this example we already had 100%, so there was no point to do that. Next step is to see if there is a gap between the training performance and the testing performance. And if there is a gap, it means there is a overfitting. In the overfitting, one thing is regularization dropout, which we have seen. Another way of dealing with the overfitting problem is, we can increase the amount of training data. So what I've tried to do in this is, I've increased the training data, which is now 50,000 instead of having only 10,000 in earlier examples. And now when I run this, you will see that the performance which we get. Okay, so this is sorry, this is not with the regularization, I guess. Yeah, so this is without regularization. So in the first model, we had overfitting, and now when increasing the training data, so what we are getting is, we are again having the overfitting model. So the point here is that adding the additional training data in the model will not always improve or deal with the overfitting problem, but it will also help. So there is a very small benefit by adding the data for dealing with the overfitting problem. So there are 5 situations. So to deal with the overfitting, first is the increasing the training data. This obviously improved somehow, and the testing performance also increased by increasing the training data. Okay, so the first thing is that we should try increasing the available training set. If it is available, if it's not available, we should go for the regularization techniques. So strong regularization is good. It penalizes the overfitting, early stopping, and data augmentation, and reduce model size. All these methods are already available. We have to try all these methods one by one and see the impact if we reduce the if we are improving the performance of the testing performance. And also observe that the gap between the training performance and testing performance, there should not be very large gap, and the model should also perform well. Okay, so this is the impact of the increasing the training data. So you can see that increasing the training set is not helping much for dealing with the overfitting problem, but surely adding regularization technique along with adding training data will help. Okay, so the point here is that not one regularization technique will always help dealing with the overfitting problem. We cannot sure that, okay, I have used L2, now there is no point of overfitting. No, this is not the point. We have to understand, and we should try different multiple regularization techniques, whatever is possible. Okay, so this is about dealing with the overfitting problem. Okay, now I will go back to these slides, and we'll try to see that what we should do, and then later on I will also explain that what we can do when we have high bias. And if you have any doubts or questions so far, please let me know. And you can also try running these codes in your collab notebook, and observe the things, and you can discuss.
So there is one question.
Yes.
How much gap in training and validation accuracy we can consider as overfitting?
See, there is no standard the ideal situation is minimum, so almost zero is the ideal situation, but in real situation it will not be there. So what we should do is uh, we should try improving the, or like reducing the gap. And what we can do to reduce the gap, we have all the methods like adding training data, overfitting, regularization, L1 L2 dropout. Okay, so all these things we should try and try to minimize. So once we have at like as minimum as possible, then we can sure. But if the graph between the training and validation loss is like loss is decreasing somewhat and then increasing for later on, so it means a clear indication of overfitting. So try to that minimize as much as possible. So there is no thumb rule like 2% or 1% should be the difference. But what I can say here is we should try to minimize as much as possible. And ideally, we should have zero difference. Okay, so 1%, 2% difference is a good one. Okay. The idea is like we should have a good generalization. So these kind of spikes is not desirable, and it should be decreasing. So this, for the example, this one, previous one. So this is okay. Still there is some spikes at epoch number 14 and 9 and all. So this is okay. So in this situation, what we can do is we can further increase the training data, and then we can try to see that what is the impact, and then also try to change the dropout value. So in this example, I have taken 0. 0.2, 0.4, 0.5 to explain the concept, and then you can also try to experiment with other values. And ultimately, this graph is a good one, except these spikes. Okay. Any other question in the chat or
No, sir, not now.
not now? Okay. Now, uh, I'll try to make all the other possible things in a sequence so that we should strategically we should try the different methods. So we know all the methods. The objective of this lab is to in what sequence all those methods should be tried on real problems. Okay, so ultimately the aim of developing a machine learning model is to uh, find out low generalization error, minimum error, and uh, on the unseen data. Okay, so if model is doing good in training but it is not performing well while predicting the real situation, so the model is like low generalization error. So that is our main aim. So one thing is, the first point is whether adding more data will always help. So this is a very common doubt that okay, when we get less performance, just add more data. So let me tell you that uh, when we train the model, if the training performance of the model is less, adding more data will not help. So for example, let's say I start developing a model, and in the first phase, my training accuracy is, let's say, 70%, 75%. So it is very unlikely. It may be possible to increase that. The adding more data may help. I'll show you. I'll let you know the reason when it will happen. But if the data which you are adding is from the same distribution as the training corpus, generally it is very unlikely that it will improve the performance. So when you have very less training performance, it will be waste of time if you try to get more data. Adding more data will help in the training when you have different kind of samples or different distribution of the data, which different representative of the original data, which is not similar. So data augmentation technique or other kind of methods to improve the training performance will very less likely is that it will improve the performance. And while if you are getting some good let's say good performance in the training time, but not good in the testing time, it means the model is overfitted. In that case, increasing the training data might help. Okay? So you can see that graph also. So just a representative graph. So if the first one is showing that, okay, this is the 4 training samples we have, and let's say now we increase the training data, it will not help in improving the training performance, because the model complexity is the important point here that is required to improve the training performance. But adding more data here will not help. Okay? And adding more data will help to reduce the variance to deal with the overfitting problem, because it makes the testing time, the model becomes like less overfit, in the sense that it will becomes more reliable and more like that the model will be smooth, in the sense that it will have a good learning representation and good generalization. So adding more data is helpful for dealing with the variance problem. Now what we can do is get more data. So as we have discussed, it will help in increasing the variance. We can try with the different features, adding different features, improving the model complexity will help in training and bias, improving the bias. And there is a trade-off. So if we increase the model complexity, we help with the bias, but at the same time there is a risk of having the overfitting of the model. So the best way is we use as much as possible features, make the model complex, and try to make the model perform as much like as close to the human performance. And then we try to deal with the possible overfitting problem by using the regularization, by using different other methods which we have discussed. Okay, so adding more complex architecture will help in reducing the bias, and less complex feature model will help like is desirable for the various problem, overfitting problem. And regularization, as we discussed, it will help in overfitting model. So this is the same thing. First is human level performance and training performance. So let's say the best performance is 100, but human can do like do the same task and get, let's say, 90% of the performance. So for example, speech recognition problem, so in which even human sometimes makes errors. So let's say 90% is the maximum that human can achieve. So our objective is or should be to make a model at least 90%, which is very close to the human level. And the performance which we get below that is the is basically a difference between human level and training error. So let's say the human is 90%, training model which we have developed is having 85%. So the aim should be to improve the performance from 85 to 90. And what we can do in order to do that is, because this is having a bias, and we should try making model bigger, train longer, better optimization, making more changes in the neural network architectures, having more features. Okay, so somehow trying to do things which will improve the learning capabilities of the model. And if once we have done that, and if there is a difference between training and validation error, so what we can do is add more training data, apply regularization because the model is overfitted, and we have to try like reducing the number of parameters and reducing the somehow, but this should be the last option, because that will somehow also drastically or significantly impact the bias. So it is like not desirable, but if we still the model is overfitted, then we can last try reducing some of the parameters and reducing the complexity of the model. But that should not be the thing which we should try initially. We should go for this method in the last. Okay, so this is the strategy. First step is that if the model is having we develop the model. If the model is having high training error, it means there is a high bias. We should try making complex model, train longer, and new architecture should be tried. And if training error is not problem, we are getting higher performance, it means there is a possibility of validation and training error differences. So it means the model is having high variance. So if that is the case, we should try getting more data, regularization, and try different architectures. Okay, and that in that also, if development error is also not a problem, so in that case, what we can do is we can try different training data more similar to the test data. And this is the step which is not always desirable, but sometimes what happens is we train the model, validate it, and develop the model, and then when we deploy it in the real situation, the test data distribution with the training data which we have used is having differences. So in that case, we have to have, like, that getting more data which is similar to the test data. Okay, so that is like a different kind of problem. But what we should do in that case is train the model, test it, validate it on some distribution of the data, but the testing data is totally different. So in that case, the performance is less, just because there is a distribution difference. Like the testing data is totally different from the training data. In that case, you have to retrain the model. And if you'll have a similar kind of distribution of the test data as training data, so you should have good performance. Okay, so this is the steps which we follow. Okay, and now I will go back to my next notebook, which is on bias. And now we'll go step by step. This is again a same problem, like minister digit detection problem. And I will just start. If you have any questions so far, please let me know.
No questions as of now, sir.
Okay. Okay, so in this, what we will do is, I have tried to make this model which is having high bias. So the model is high bias if the model is very simple. So in that case, what I would try to do is, I've developed this model with very less number of parameters. So only one layer of 5 nodes. You can try with 5, 10, 15. That is also giving very low performance. But for this experiment, I have taken only 5 nodes. So it is a clear indication that the model is very small, and it is having very less training performance, and it is very underfitted model. Okay. Apart from that, everything is same. We are taking imaged images, normalizing it, and we are taking only 1000 images for training and 2000 images for validation. Yeah, and we are not using any dropout or L2 regularization. So it is a simple architecture. Okay, and now we'll observe the performance. So you can see the training accuracy is starting from 13%. Just because we have made this model very less complex. So training performance is the number of parameter which we have taken. The network is not able to learn the patterns in the images, and it increases somewhat up to 79%. Okay. Okay, just I'm just stopping here and going back to this point, and I just forgot to uh, talk about that performance difference. So one point I wanted to explain is, in the overfitted model, we got 96% of accuracy, but when we have made regularization, overfitting, dropout, everything we have solved, and the model was well generalized, but still the performance was less as compared to the overfitted model. In that case, what we should do, because the performance which we are getting with the overfitted model is higher, but not overfitted model, it's low. The solution, like my perception on this is because the training data is the model which is the overfitted model is it is giving 96%, which is 1% higher to the well developed model, is not desirable because that is by chance for that particular test data in one sample is like you are getting 96% of the accuracy, but eh, this is a more generalized model which is having no overfitting symptoms. So in that case, this is desirable because it is having stable performance. It is just like for let's say some other real-time test data. So the first model can like might give different performances, but this will surely give you very near to the 95% of accuracy. So the overfitted model, the first model which give 1% higher for this example, but like if we try to have a different portion of the test data, it might get to like 88% or 90%. So that is why it is always important that the model should be low variance. Okay. Now I'm sorry to go back there. I just reminded that concept that I wanted to explain. Now coming back to this bias problem, you can see that okay, so the performance, training performance is 79%, which is very low, and validation accuracy is also low, and accordingly losses for the training and also not as desired. So you can see that it is decreasing. Okay, now you might have think that okay, this is there is a high bias, but it is just because, not because of the model is complex, but because of the number of epochs. Because it is decreasing, it may further decrease and make model like better. So in this situation which we have developed, the model which we have developed, first thing is we have started with one network. Now what we should do, so the first thing is what we can try, that in the first tense we can see that the training loss is decreasing and further decreasing, and we are stopped in between like after 50 epochs. It means that there is still a possibility that if we increase the number of epochs, the training performance can increase and validation accuracy or performance can also increase. The first step we should do is instead of directly going to increase the number of nodes and the parameters in the model, making the model complex and so on to have like biases. First thing is that what we can do here is we can further improve the number of epochs. So at least we are giving sufficient number of samples and number of epochs for the training. So what we can now try is I have run this code for 150 epochs, okay, with the same network. And now if you'll see, now you will see that testing performance is not improved much. Training performance has increased up to 90%. And in the graph, you can see that with very small network, still very small network, but there is very good training, almost 90%. And testing performance on the validation data also decreased. After some time, it became flattened. But this is it's a case where we have low training, low performance. So there is basically high bias and high variance situation. So third example which we have seen in the first in the slide, that when the model is high bias and high variance, so the model is needs to like we have to deal with the bias. For dealing with the bias, first thing which we can try is improving the network complexity or the model complexity. Okay. So in the next example, what I'm trying to do is I'm increasing the number of nodes. I made 50 nodes instead of having 5. And apart from that, everything is same. Number of epochs, again, it is 50, just to see what happens if we compare with the first experiment. and then see that after increasing number of nodes to 15, the training performance reached to 90 and testing performance is increased to 83. So you can see that there is very smooth declining in the training loss and the validation loss, but still you can try improving or increasing the number of epochs. And it is also there is again the gap between the training loss and the validation loss, so it is again a high variance situation, and also a high bias, because 90% is the training performance, which is not as compared to the human level performance. So we should try improving the like bias and training performance also. Okay, so now what we can do here is further increase the number of parameters, number or number of layers, or number of nodes in the each layer, and so on. Okay. So here now I increased to number of nodes in the first layer is 32, and then try to train this model, and you can see the training performance further increased to 92%. Okay, so 92% is like somehow improved, and testing performance also improved, and you can see that the difference is also further improved. So this is the process that we are trying to improve the training part. We are not like focusing on the testing part as of now. The first step is we should focus on the reducing the bias by increasing the model complexity. And as after some time, what will happen is it will increase so much, like now from 5 to 10, 10 to 30 to 15, then 32. If you'll increase it to, let's say, 512 as our previous example, so it will become almost 100% training performance, but the model become there will be no bias, but the model become overfitted. So there is a trade-off. We have to, see, by increasing the model complexity, it will somehow deal with the bias, but at the same time, it will also increase the chances of overfitting. But we have to go in steps. First, we have to focus on the dealing with the bias, and for dealing with the bias, we should try to like try all the methods which I've seen by making the model more complex, and trying to understand and learn the parameter information and the features of the data. Now in next, I am using 128 features nodes in the dense layer. It is not training performance is increased to 94, but testing and validation performance is not increased. There is still a gap, but training performance is increased. It means the model become more complex, bias has reduced, but not the variance. So we are not focused. We should not focus on the variance or the testing performance for the as of now, because our focus is on improving the training part, reducing the bias. First, we should always try to reduce the bias. We should not bother about the variance at this point of time. Okay. Now I have tried different architecture. Instead of having one layer, now I'm trying to have multiple layers, 2 layers in 32 nodes each, and now it is almost same, but not help much. So maybe having 2 layers of more parameters will help. Yeah, this is the same one. Yeah, so in this example, I have changed the optimizer. So making the different like better optimizer has helped with the small parameters also. So for this, again, I've run this, and you can see that the training performance has increased further. And when you see, okay, now the model has become overfitted. The training is good. Now model is become overfitting. Okay. So now first objective is achieved. What we have done is we have achieved, like we have a good optimizer, good good network, number of parameters are also good, and we have achieved very good training performance. So it means there is no bias here. Now, once there is no bias, what we should do is we should go for the dealing with the overfitting. And for the overfitting in the first note sheet notebook, we have seen that we can try reducing the like variance by having regularization method L1, L2, dropout, okay, and also having adding more data. And we have seen the impact of all these methods on this sample data and network. And what we can do is we should go in the sequence. Whenever we train the model, first try to reduce the bias, then all the methods which we have in the bias that we can try, and then we can try reducing the variance, which is possible that when we try to reduce the bias, there is a possibility of having variance to be included in the model. So model can become overfitting, so that we can try to reduce with different methods. So for you, I have just compiled that what we can do for having dealing with the bias, that model increase model size, feature size, eliminate regularization if there is, but in if it is not there, it's okay. Modify the architecture for variance, adding more data, regularization, early stopping also a method that if you have trained it for a long time, so you can stop early, so making the model learn generalized features and all these things which I have made for you. All these things is just for your reference. I'll share these slides with you, and all the things which is written in the slide, I've tried to explain it with the notebook. And there's some last guideline is like you should choose development test data that reflects your expectation. Sometimes what happens is we train the model, and then we see different kind of test data in real time, so in that case it will not work. And it should be from the same distribution, and we should also have sufficient development validation data to see the differences in the model, and to see that what is the that what is the best parameter should be, and accordingly for training purposes there should be sufficient validation data also. So I think I will now stop here. Please let me know if you have any questions. And I think next lab sessions will be on uh, other topic, transfer learning and fine tuning, that Priyanka madam will take care. Any questions or any thoughts on what we have discussed so far? Hello, am I audible? Priyanka madam?
Yes, sir, you are audible.
Okay, so I have done. If anyone else, if anyone is having any questions, please let me know. Otherwise, I think we can start discussing another lab session on transfer learning and fine tuning. Madam, you are not audible, madam. Not audible. You're not audible.
Hello, am I audible?
Yes, yes, madam.
So thank you so much, sir, for a wonderful session. And mm, uh, sir has already shared the code in Collab with you all, so you can access it through that. Now I think we can move on to our next session, lab session on transfer learning. So for that, I request Rinky to present her screen. So she will be talking about transfer learning and fine tuning with respect to convolutional neural networks in the image data sets. There will be a separate session on convolutional neural networks, which will be taken by Professor Rajesh on Thursday. Meanwhile, in this session, we will only see the use of how to implement the transfer learning mechanism and how to fine tune it as per your need.
So, hello, am I audible?
Yes, you are audible.
Thank you, ma'am. So, I will start with the transfer learning implementation. We will take our base model as VGG16. It is a benchmark CNN in machine learning area. So we will, what we will do is, we will train first VG16 with the data of X-ray images, of tuberculosis X-ray images. Then we will save it after training, and we will use this saved model as a pre-trained model for our another data to do transfer learning. Like we will do everything from scratch. We are not taking VG16 directly for transfer learning. We are training it and saving it. Then we will take it for the transfer learning. Then we will do transfer learning with another data in the same way which we have learned in the session. So let's get started. So these are the libraries. First is the TensorFlow.Keras. So TensorFlow is the open source platform for machine learning, and it provides the tools for building DNN and models. And image data generator, you all know that it will import the images from the directories and do the data augmentation and provide the images as our requirement, input requirement. And another is in the model sequential, will import the model architecture and sequential in the order, and dense, latent, dropout are the layers, and Adam optimizer, and model checkpoint is for saving the history of our training in a file. We will show this later on, and these are things. So I will start with first, these data will be provided to you. So this data is uploaded on my drive. So when I run this cell, the data, the drive cell will be appeared here, and we can select, we can copy the path of the data file and paste it here. So just load the data on your drive, which will be provided to you, and run this cell. And in this here, you will see the drive file and copy the path and paste it here. So we will divide data in this data. It will the OS module which take the file. It is used to navigate directories, check path, and load files. So it will directly load these files and transfer it to the train directory in this. So we have imported OS here for these things. So this is a module in Python, and image size is defined because the 16 has a standard input of 224. So we have defined it, and batch size we have taken as 32. And now we will do generate the images and do the pre-processing task. So in train image data generator will take the images. The pre-process input will do, it will ensure that image pixel will normalizes, and it will pre-process your inputs to match what VGG16 expects as input. So it will ensure that. So train these all three files have the data in that way. And now .flow from directory will take the data from this directory and will take the data as we provided the features like target size will be that, and test size will be that, and class mode will be binary, and in test data we have also provided the test directory, and shuffle false equal to false will ensure that the test data will be provided as it is, like it will be not shuffle as it is, like if first image is one image as first place, it will be going at first place. The if any image is at 10th place, it will be going at the 10th place. So test data will not shuffle, and these are the details of the data set. So now we will create our model. So model is VG16 and weight equal to none we have taken. So this model will generate their own weights from random, and that VG16 will train from scratch and include top equal to false, because in VG16 model there are some dense layers on the top, but it is defined according to the ImageNet data set. So that's why we have removed it, because we are taking another data. So include topical to false will remove the head of the model dense layer. It will only consider the convolutional layer. So VG16 will act as a feature extractor of for your images, and input shape is which is the required for VG16, and model.summary will produce your summary of model. So these are the layers in VG16. So we have cut after the max pooling 2D, we have cut the top layers by include top equal to false. So this is the model till now. Now if we train it, the output is not as required. So we have to add some output layer in that. So now from TensorFlow Keras, we have imported global average pooling, 2D dropout, and dense layer, and X will take model dot output. So what is the output of that model? The model is our variable of this model. So X will take model dot output, the output from this model. And again, this X will insert it on global average pooling, which will reduce the featured maps and to the one-dimensional vector. So if the output is 77512, it will reduce to the only 512. And now this X will transfer from the dense on the dense layer of 256 neuron with activation ReLU, which is a fully connected layer, and this X will transfer on the output. So this is a one by one performing layers, and the final model will be model. This model will create model by inputting input the model dot input and output. So model it will take from the input of the this model and till this layer, and it will take these layers which we have defined also. So we again type model dot summary. Here you can see that in a previous model we have till here layer till here, and now we have we have added global average pooling and dense layer and a output layer with sigmoid activation because this is a binary data. Now we will compile the model with optimizer Adam, and learning rate defined, and loss is binary loss entropy, and matrix is accuracy. So now we will what we will do, we will train our model. So model checkpoint is a callback in Keras that allows you to automatically save the best architecture and best weights of your model. So checkpoint, a model checkpoint is a module in TensorFlow library. So we will call this model checkpoint. We will provide a file path so that the architecture and weights will be saved in that file. This file, whenever you run it, after this whole process will be done, try here. This file will be appeared here. So you can download it and copy it. So for further uses. So our written model is this, and the monitor is what quantity we want to monitor. We want to monitor your validation loss. You can also provide validation accuracy or training loss, but validation loss is is a standard quantity to monitor. So we have taken validation loss and see that that's only so where the model provides the best performance. This will save the best weights where the validation loss is minimum. Best is for monitor validation loss and mode is minimum will provide the model that it will save the minimum validation loss for every epoch. So save based only means whenever the validation loss is minimum, it will save the these weights. And save weights only false means it will save the full model, like architecture of model also, which layer is connected to which layer, and the weight of every layer also. So it will save the whole model. And by was equal to 1, the print the all these things. And the model dot field, you are already aware of it. This is for the training. And callbacks equal to checkpoint will create a list which tells the model that after each epoch, the model checkpoint that after monitor. So after every epoch, it will call the monitor. So not my no. So hope you have a what we have thing or 50 we have included the model dot evaluate function will return us the loss and accuracy. So test and test accuracy will be assigned by the model dot evaluate function for test and gen data. And this is the test loss and test accuracy for this data. The previous saved model as a base model.
Hello.
So yes, ma'am. Hello.
Hello. Yeah, Rinki, you were not audible for the past 1.5 minute. 1.5 minute.
Okay. The past 1 minute.
Now
So
also
after
the
the
wait. No, the voice is breaking. Am I audible to you?
Yes, ma'am, you are audible fine.
Okay, now you are audible.
Okay.
Hmm.
Okay, so after the training, what we will do is we will evaluate the model. That model dot evaluate will return this definition will return our test loss and test accuracy. So this will assign in these two variables, and we will print the test loss and test accuracy. So these are our results. So uh, till far we have what we have done is we have trained our VG16 architecture on an X-ray maze data set, and we have saved the model as you have seen here, transferred VG16 TV model dot keras as file. So we have downloaded. I have already downloaded it. You can run and try to download it. And we will treat this model as a pre-trained model, so as a feature extractor only. And then we will add some layers to the head of this model and do the transfer learning part from this model. So here we have done some data augmentation, which is control augmentation, which only improves generalization and not increasing the data. So this is necessary because if in trained data set we are not inserting image as it is. We have defined some things like zooming it and shifting it from there, so that the model generalizing it and take the data as diversity of the data. So in test data, if there is any other feature of in the image, it can also be taken by the model because it is trained on augmented images by zooming and flipping and shifting parameters. So this will provide generalization in the data only. So again, we have by the means data generator, we have defined the data generation file and validation file and testing file. So this is our another data. Again, this is in my drive. So copy the path and paste it. Again, OS will take this train validation and test data set in the files, image size, test size. Again, it will take these flow from directory. It will take these files as the target size and base size and the class mode. So now we will import the model, and load model will command allow us to load the model which have saved in a .h5 file or .keras file, and then select and drop out as the layers. So what is pre-trained model? Pre-trained model which we have shaped before. So this file we have saved. So when you have saved, and if you, let's say, if you want to run after some time, then you can upload it this file from here. You can upload it and copy the path and paste it here. So the now our pre-trained model is this, which is a previous model which we have trained on tuberculosis dataset. And the pre-trained model summary is exactly same which we have shown. So now this we will add some more dense layer and drop out for the transfer learning of this data set. So uh, this is the output layer. We are not required, because after this nothing can be done. So what we will do is we will take output of this layer, which is a dense layer. So feature output after pre-trained model dot get layer will get the layer which will be provided here. You can try to get different layer. Like if you provide block 5 pool, it will take the output of block 5 pool layer. So it you can provide the name under the codes in this. So it get layer dot output will get the output of that layer. So now output of 2, and again after that we have one trait neuron layer, then again the dropout, and the last layer or last output layer is sigmoid function for the binary classification. So TL model will design the transfer learning model here. So it will take the model from inputs to output, which is X. So TL model summary is as shown here. So after this dense 6, we have added 2 layers. One is dense, one is dropout, and the output layer. So it has been shown. So now there we have if you remember in the today's session we have learned the fine tuning, the partial fine tuning and the full fine tuning. First, what we will do is we will freeze all the layers in the pre-trained model and just train these head layers, which are these last dense layers only. So for a layer in pre-trained model dot layers, so it will take all the layers in pre-trained model only, which is from for here. So layer dot trainable equal to false, it will be not trained. So from TensorFlow Keras Optimizer, it is import Adam, and TL model will compile with this optimizer and method accuracy. So it will only train the last 3 layers, which we have last 2 dense layer, which we have added, and it will. This model will be saved as a transfer model .h5 file. You can save your model at .h5 or .keras file. Both can be acceptable, and the same save best only and history. So now the transfer learning has been done, and accuracy has reached up to this 74% only, and the test accuracy is very less. So now what we will do is we will do the fine tuning of this pre-trained model also. So again we will download the model and load model of the transfer model.h5 which we have saved, and we have done a partial fine tuning here. So up to 4 layers, what this will do, that the first 4 layers it will not train. Layer dot trainable is false, and after the first 4 layers, it will train the layers of the transfer model of the pre-trained model. And for full fine tuning, this has written that you can take all the layers and layer dot trainable equal to true. It will take time, so you can try it for the full fine tuning and the partial fine tuning also. So model dot compile will compile the model, and again we will do the early stopping and the checkpoint. It will monitor the validation loss. So in this, what we have early stopping is a new thing here. So in early stopping model, what we will have done is we will monitor the validation loss, and patience equal to 5 means if to 5 hooks, the validation loss will not improve. Improve means it will not minimize, it will stop. So that's why, and it will restore the best weights, best weights up to now. So that is the early stopping will do, and the checkpoint is same. So again, we will history underscore fit will train the model for the fine tuning, and we have taken learning rate very minimum because fine tuning requires lower steps. So this is our training up to 20 pokes, and you have seen that accuracies increase very much, and this restoring model waves from the end of the best epoch. So best epoch is 18. The more validation loss is minimum for the 18 epoch, and the validation accuracy has improved for 80%. So this is what fine tuning has been done to the model, and this is all the thing of the transfer learning and fine tuning. Now, after this, we will add a sequential model transfer learning for with enhanced classification add. So, as of now, we have only added 2 layers. Hello.
Yes. Up till now, any doubts? If there are any doubts, you can ask. We can take some 2-3 minutes break, and if you have any doubts, we can listen to the doubts. So in the morning session, you saw the demo of transfer learning in with application in natural language processing that was on the text data, and in this session, you are seeing the application in image classification. So I hope whatever you have seen in the theory in the first session taken by Ms. Tanya Garg, you can relate it here in this lab session. Now we are moving to something called a sequential model transfer learning. Before moving ahead, if there are any doubts, please feel free to write it on the chat box. Else we can continue in 2 minutes. All right, we can now move ahead with the sequential model transfer learning with enhanced classification head. So we are taking the same example and showing the demo of sequential model transfer learning.
So all these things are same in this part also. Just we have enhanced the classification head by adding some different layers, and which will enhance the classification of the data. And by adding only 2 layers, will the results are not as up to the mark. So we have to add different layers and do the fine tuning. And these are all these things are random. So you have to take it upon a task. So you can try on your own data set also of this transfer learning task. So we will again do the trained data gen image data generator. We will, and this will take the data set by shifting and zooming images, and again the validation data gen and test data, and again this data will be uploaded. And so this is our the pre-trained model which we have run in the first part only. So V16 TV model.krs, if you remember, and this is the pre-trained model summary up to this. So after this, what we will do is we will take the output of this layer, because we only want to select the convolutional layer of this pre-trained model. So feature output will take the block 5 pool layer output, and after this we will apply the global average pooling duty to reduce the feature maps to a one-dimensional vector. And after this, batch normalization will apply to normalize the pool features after global average pooling, which is necessary. And after this we will apply the dropout, and after this we will again add a dense layer of 256 neurons, and after this we will apply on this dense layer we will apply activation. We have taken leaky ReLU here. You can take according to your requirement. So after this, we will apply batch normalization. If you remember, the leaky ReLU will act in a model as a separate layer, not directly in the layer as ReLU. So ReLU can be inserted directly, but leaky ReLU will act as a different layer. So after this, again dropout and a dense layer with standard ReLU of 264 neurons. After this, again a dense layer, again now the output layer of 1 neuron with activation sigmoid. So this model will be saved in this variable SETL model, which is sequential transfer learning model, and inputs will be taken from the pre-trained model dot input, and outputs are X. So sequential transfer learning model summary has been given here. So after the block 5 pool, we have added these layers in this. This is the sequential model transfer learning, sequential model of for transfer learning. So for firstly, we have trained this model by not training the pre-trained model. So layer dot trainable equal to false. We are training only these layers. After that, we will do fine tune, and again compiling again the model file will be model.h5, and for it will run for 40 folks. And after that, we will do fine tuning. So again, load the model which we have saved, and for fine tuning, we will take up to 3 layers free, and after 3 layers, we will unset and compile the model. So after that, we will using same checkpoint functions and model and train data, validation data, and callbacks. And after that, so the accuracy has increased, and in previous on without sequential model we have 80% accuracy, and here we have 82%. So this has increased the accuracy after if you apply different things which you have learned, like the overfitting techniques, and there are some things which is hyperparameter tuning and all, and reduce learning rate schedulers, then we can also improve the task, the classification accuracy of this task. So you can apply these things in the trial, which will cover all the topics of which we have learned in the session or today's session. So, and it will be more understandable for you. So if you have any doubts till now, you can ask me.
We will be sharing all these files on the Canvas portal. So if you have still not accessed the portal, kindly access the portal for all the course materials. So we will wait for 5 more minutes for the doubts. Meanwhile, the participants can fill out the feedback form. Okay, so I think there are no questions. So we will end the today's sessions and the day today. I have shared tomorrow's schedule on the WhatsApp group. Please refer to that and join accordingly. Also, make sure to fill the feedback forms. Thank you very much for joining. See you at 9 a.m. tomorrow.